Last class we discussed solubility of solids in liquids. Solubility, saturated solutions, such things we discussed. And today we can see the solubility of gas in a liquid. Last year we discussed a particular law known as Henry's law. You may remember it. The quantity of a gas dissolved in a solution is directly proportional to the pressure applied on the surface of the liquid. That is a statement that we have studied last year. That law is almost correct because the solubility of gases increases with increase in pressure. So pressure has a major role in the solubility of gases in liquids. At a high pressure, more amount of gas will dissolve. So here from the diagram it is very clear. In the figure A and figure B, when you compare, B has higher pressure, there you can see the concentration is high. Or concentration is more in the case of B. So the solubility increases with increase in pressure. But if we study it in detail, in the detailed study, we can see the mole fraction of gas dissolved in a liquid is proportional to the vapor pressure of the gas above the liquid. So Henry's law modified in such a way that the mole fraction of a gas in the solution is proportional to the partial pressure of the gas over the solution. Mole fraction of gas. Instead of the quantity, we changed it into mole fraction of the gas in the solution is proportional to the partial pressure of the gas over the solution. Instead of the pressure applied on the surface of the liquid, we changed it to the partial pressure of the gas over the solution. So what is Henry's law? Henry's law states that the mole fraction of gas in the solution is proportional to the partial pressure of the gas over the solution. P is equal to kH into X. P is the partial pressure of the gas over the solution. kH, a constant known as Henry's law constant or Henry's constant. X is mole fraction of component. And here in this graph, partial pressure is plotted against mole fraction, and you know, mole fraction is directly proportional to partial pressure. You will get a straight line graph. And this Henry's law, it is an important law which will help you to identify the solubility of a gas in a liquid. Higher the value of kH at a given pressure, the lower is the solubility. And if a particular gas have very low kH value, we can say the solubility of gas in the liquid is very high. The solubility of the gases increases with a decrease in temperature. We know as the temperature increases, the kinetic energy of the gaseous molecules will increase, and that will overcome the attractive forces from the solvent and will go to the vapor state. Therefore, with increase in temperature, the solubility decreases. So we can say aquatic life is more comfortable at low temperature or in cold water. The reason, there will be more amount of dissolved oxygen. The Henry's law finds several applications, a lot of applications. Here we will discuss three major applications of Henry's law. When we make carbonated drinks, in order to increase the solubility of carbon dioxide, we'll apply high pressure. So to increase the solubility of carbon dioxide in soft drinks and soda water, the bottle is sealed under high pressure. When you open the soda bottle, what happens? Carbon dioxide comes out quickly. That is due to the decrease in vapor pressure. The pressure decreases, therefore carbon dioxide gas evolves quickly. Another important application, in the case of scuba divers, they are taking cylinders, oxygen cylinders with them. Otherwise, in deep sea, they cannot breathe. But when they are carrying the cylinders, if it contains liquefied oxygen, large quantity of nitrogen will be present in it. So at a very high pressure, in deep sea water, the pressure will be very high. At very high pressure, nitrogen will dissolve in water. Otherwise, solubility of nitrogen is very low in blood. So at a very high pressure, nitrogen dissolves in the blood along with oxygen. Oxygen is needed, but nitrogen is not needed. So when the diver comes to the top, the pressure will decrease. As a result, the dissolved nitrogen will evolve. The dissolved nitrogen in the blood, that will evolve. That causes some painful effect on the divers, and that condition is known as bend. So to avoid bends or the toxic effects of high concentration of nitrogen in the blood, the tanks used by scuba divers are filled with the air diluted with the helium. About 11.7% helium will be mixed with the air. That is to decrease the mole fraction of nitrogen in the mixture. If the mole fraction of nitrogen in the mixture is very low, its solubility also will decrease, because the solubility of nitrogen in blood is directly proportional to its partial pressure. So if in the mixture its concentration is very low, its partial pressure also will be very low. Therefore, it is mixing with the helium. Another important application at a higher altitudes. Higher altitudes, the pressure is very low. Therefore, solubility of oxygen is less than that at the ground level. This leads to low concentration of oxygen in the blood and tissues of people living at high altitudes or climbers. The oxygen level will be low. It causes climbers to become weak and unable to think clearly. They will become very big and they cannot think properly. Symptoms of a condition known as anoxia. That condition is known as anoxia. Breathing problems will arise due to low concentration. So these three are some of the important applications. What is the first one? Carbonated drinks. That is bottled at a high pressure. That is to increase the solubility of carbon dioxide. Second one, to avoid burns, the oxygen tanks, that is liquefied air, is diluted with the helium. In order to avoid the toxicity of nitrogen, increase the concentration of nitrogen in the blood. And the third one, the anoxia. There is possibility of anoxia that arises due to low level of oxygen in the blood and tissues. Those who are living in the mountains, or in the case of mountain climbers, if the pressure is low, solubility of oxygen will decrease. Now, Some problems related to Henry's law. The mole fraction of helium in a saturated solution at 20 degrees Celsius is 1.2 into 10 raised to minus 6. Find the pressure of helium above the solution. Give Henry's constant at 20 degrees Celsius is 144.97 kilobar. This is a direct question. What is the equation? Partial pressure of helium is equal to Kh into mole fraction of helium. Phe is equal to Kh into X. What is Phe? That is equal to Henry's law constant into mole fraction of helium. Henry's law constant 144.97 into 103. Sorry, here there is a mistake. 10 raised to 3. 144.97 into 10 raised to 3. 10 raised to 3 is to convert kilomoles, kilobar to bar. That is not 103. 10 raised to 3 into mole fraction 1.2 into 10 raised to minus 6. It is 1.2 into 10 raised to minus 6, and that is equal to 0.174 bar. A direct problem. Now, index to problems that is solved in the description. When it is described in the Victor's channel, it is solved. What is the first question? H2S is a toxic gas with a rotten like smell. Is used for the qualitative analysis. The solubility of H2S in water at a tip is 0.195 molal. Calculate Henry's law constant. Here also the question is P is equal to Kh into X, or X is mole fraction. And here what is given? Molality is given. 195 molal. 0.195 molal, that is given. So here we have to convert it into number of moles. 0.195 molal, that is equal to 0.195 mole per kilogram of water. 0.195 mole of H2S is present in 1 kilogram of water. 1 kilogram of water means 1000 grams. 1000 grams divided by 18, that is equal to 55.55 moles. Number of moles of H2S into 0.195, and number of moles of H2O, NH2O, W by M is equal to 1000 by 18 is equal to 55.55. Mole fraction of H2S, X is equal to NH2S divided by NH2S plus NH2O equal to 0.195 divided by 55.745, nearly equal to 55.55. That is equal to 0.0035. Now it is very easy. Substitute the values and find out the value of Henry's law constant. Kh is equal to P by X is equal to 1 divided by 0.0035 to 285.7 atmosphere. Now the second question. Henry's law constant for CO2 in water is 1.67 into 10 raised to 8 Pascal at 298 Kelvin. Calculate the quantity of CO2 in 500 ml of soda water when packed under 2.5 atmosphere. CO2 pressure at 298 Kelvin. So the pressure of CO2 at 298 Kelvin is given as 2.5 atmosphere. So we have to convert it into Pascal. What is the reason? Henry's law constant is given in Pascals. So we have to convert the pressure of CO2 in Pascal. This one also solved in Victor's channel when it is described. So Kh is equal to 1.67 into 10 raised to 8 Pascal. Partial vapor pressure of CO2, 2.5 atmosphere, that is equal to 2.5 into 101.325 Pascal. Volume of solution is equal to 500 ml. That is equal to about 500 grams. 500 ml is about 500 grams. Then Henry's law, P is equal to H into X, mole fraction of CO2, X is equal to P by Kh, 2.5 into 1,01,325 divided by 1.67 into 10 raised to 8 is equal to 0.001517. and number of moles of CO2 divided by number of moles of H2O plus number of moles of CO2, that is mole fraction of H2O. And in this equation, it can be nearly or approximately written as NCO2 by NH2O. Number of moles of CO2 by number of moles of H2O. So mole fraction 0.001517 equal to number of moles of CO2 divided by number of moles of H2O, that is 500 by 18, equal to number of moles of CO2 divided by 27.78. So number of moles of CO2 is equal to 0.001517 into 27.78 is equal to 0.04214 moles. That is the quantity of carbon dioxide dissolved per 500 ml, 0.04214 moles. Or we can convert it into grams, number of moles into molecular mass. That will give the mass. So 0.04214 into 44 is equal to 1.854 gram. So it is enough for today. So we can discuss the remaining topics in another video. The remaining topic is about the Raoult's law. So next class we can